If I say I want to compose these two functions, where f of x is x squared and g of x is x plus 1, what composing means is I put one function inside of the other function. There's a YouTube video that's like 20 years old now, but I remember it pretty vividly because I was like in high school when it came out. And back in the early days of YouTube, this got a lot of views. It was a video of a guy that was preparing for Thanksgiving, but he was going to make a turducken, and he started off with like a quail, and he stuffed that inside of the cavity of a duck, like where in the part of the bird where you normally put the stuffing. Like put that in a duck, and then he put the duck inside of a goose, and then he put the goose inside of a chicken, and then he put the chicken inside of a turkey. And so the turkey didn't have stuffing inside. It had like 4 other birds that were like Russian nesting dolls. That might be kind of a gross example, but whenever I think of function composition, that's immediately what I think back to. I think about the turducken YouTube video of that guy making his turkey. Well, anyways, if I say f composed with g, this is what I mean. I'm taking the f function, and then where I would normally have the argument, or the input, those are synonyms. If I use the word argument, I mean the input to the function. Where I would normally have the argument of the function, instead of saying my argument is going to be the variable x, I'm saying let's swap out x for this whole function g of x. And so if f of x is x squared, then f of g of x is going to be g of x squared. And if g of x is x plus 1, then this is the same thing as x plus 1 squared. Does that make sense? Okay. Function composition is not commutative. With addition and multiplication, those are commutative, so that means the order doesn't matter. It doesn't matter the order you add or multiply things in. Function composition is not commutative, so that means the order in which you compose functions does matter. And so if g is my outside function and f of x is my inside function, well then I think g of x is x plus 1, g of f of x is going to be f of x plus 1. And since f of x is x squared, then g of f of x is x squared plus 1. It's not the same thing. Is everybody good so far? Okay, so when we do function compositions, we have an outside function and an inside function. So now we've got just another example that we can work through really quick. Right now I care about what is f of g of x, where my f of x function is the sine function, and g of x is this rational function, x squared over 1 minus x squared. So what is this composition going to be?
Would be sine of x squared over 1 minus x squared.
Perfect. Yep. So this is sine of g of x, because the f function is just the sine function. And then since g of x is x squared divided by 1 minus x squared, then you're right, that's exactly what we get. And then let's do the composition the reverse way. Now let's take g of f of x. And what is this going to be? Hudson?
So it'd be like sine squared x over 1 minus sine squared x.
Perfect. Yeah. And so the g of x is x squared divided by 1 minus x squared. So this is going to be f of x squared divided by 1 minus f of x squared. Everywhere I see an x in my original g function, I now have to replace it with f of x. And then Hudson is right. This is going to be sine squared x divided by 1 minus sine squared x. Is there any way I can simplify this any further? Yeah?
I think it's tangent squared x.
Yeah, you're right. So the first step in simplifying this even further would be to say, I know a particular trigonometric identity where cosine squared plus sine squared is equal to 1. That's in your little booklet of stuff you're supposed to memorize. This comes from applying the Pythagorean theorem to the unit circle. So where the hypotenuse is always 1, the side lengths are cosine of x and sine of x. And so like the Pythagorean theorem says, a squared plus b squared equals c squared. Well, if c is 1, then c squared is also 1, and a and b are sine and cosine. So then, cosine of x is 1 minus sine squared of x after I subtract sine squared from both sides. And that means the denominator is the same thing as cosine squared. And then, since tangent is sine over cosine, this is the same thing as tangent squared. Okay. So I would really encourage you to be super duper familiar with your trig identities, because that can help a lot of times in making derivative calculations easier. So here's a different kind of question. This is now exercise 2 on your homework. And it's phrased a little bit differently. It says, rewrite the following function as a composition of two simpler functions. And what I mean is I'm showing you y equals a composite function. There's an outside function and an inside function. And I just want you to identify what is going to be the outside function that we'll call f, and what's going to be the inside function that we're going to call g. So what's the outside function here?
Secant x.
Yeah. The outside function is just going to be plain old secant of x. And the inside function is
X cubed.
x cubed. Okay? So that way, whenever I compose f of g of x, this is going to be secant of g of x. And that's going to be secant of x cubed. And that's exactly what I wanted to start with, right? So it's an important skill in this class to be able to look at a composite function and know what would the outside function look like, what would the inside function look like. How are these composed to create secant of x cubed? We'll do one more and we'll move on. If I have natural log of x squared plus 1, what's the outside function? Yeah, and what's the inside function?
X squared plus 1.
Perfect. Okay, I'm going to take a pause for a minute, let everybody catch up on notes. But are there any questions about this before we move on? Differentiating between what's the outside, what's the inside? Okay. So this is called the derivative chain rule. Again, this is already typed out for you in your little packet of things you must eventually memorize. And the derivative chain rule says this. If I've got a derivative of a composition of functions, so I'm taking the derivative of f of g of x. F is my outside function and g is my inside function. Then this derivative is going to be f prime of g of x. So notice I took the derivative of only the outside function, but I left the inside function alone on the inside, times g prime of x. So that's the derivative of the outside function times the derivative of the inside function. Okay? Okay, so let's try it. When I look at this one, the derivative of e to the power 3x, I'm thinking the outside function is e to the x. The inside function is 3x. So if I compose f of g of x, I get e to the power 3x. F prime would be e to the x, and g prime would be 3. Perfect. Yep. And this should be an easy one, you guys. 3x is the same thing as 3x to the 1 power. So bring down the 1, and you've got 1 times 3 to the power, times x to the power 0. But of course, x to the power 0 is just 1. So if you see a constant times x, then you just get rid of the x. That's the derivative. If you saw 5x, the derivative is 5. Okay. So now we're ready to write the derivative. As I'm going to have f prime of g of x. And so this is going to be e raised to the power 3x times 3. And a nicer way to write this is with the constant multiples out front. And so the pretty way to write this would be 3 times e to the 3x. And over time, you'll get to the point where you've practiced enough that you don't have to write down all of this stuff, right? Like you practice, you get enough practice, and you start thinking derivative of the outside function times derivative of the inside function. And instead of having to write down f and g and f prime and g prime, you'll just start to do it. That's the goal, right? Whenever I pass out a homework and it's got like 50 derivatives on it, again, I'm not grading your homework. But it's really, really highly recommended that you get all of that practice in, because the more you practice, the faster this is going to be, and the more consistent you'll be able to get the derivatives right. A lot of you guys play sports, right? I used to play tennis. One of the things we would do in tennis class is we would just do drills. And everybody's worst skill among all of the tennis skills that you could have is backhands. It's really hard for whatever to hit a backhand shot. And so we would do drills sometimes where we just spend hours hitting only backhands, right? Coach or the ball machine would just hit balls to our backhand. And we just sit and do that over and over and over again for hours. And it sucked. But the point was, if I practice that for hours and hours and hours, then when I'm in a match and it matters, I can do it quickly, I can do it consistently, I'm not going to hit the ball out. Same thing here, right? Pretend like you're practicing. The more you do it, the better you're going to get. So let's take a look here. I've got derivative of natural log of 5x. So the outside function is natural log. The inside function is 5x. So what's the derivative of natural log? 1 over x. And so I'm going to write 1 over 5x, because I'm going to leave the inside function alone, times what's the derivative of the inside function? 5. And of course, I've got a 5 in the numerator and a 5 in the denominator. Those cancel each other out, and this derivative is just 1 over x.
Is that how it's going to be for everyone? If it's like natural log times whatever? If it's just a...
Oh, you're right. So it doesn't matter what I multiply times x. If I've got natural log of a constant times x, then the derivative is always 1 over x. You're right. And if you are really keen on your properties of logarithms, there is a particular property of logarithms that says this. Whenever I'm multiplying two factors inside of a logarithm, I can split that up into two different logarithms. I can call this the same thing as natural log of 5 plus natural log of x. Do you remember that from college algebra?
Yeah.
From pre-cal? And so now, taking the derivative of natural log 5x should be the same thing as taking the derivative of natural log 5 plus natural log of x. This derivative is 1 over x. And this is just a constant, right? There's no x's here. This is just a number. And the derivative of a constant is always 0. The derivative of a constant is always 0. And so I've got 0 plus 1 over x, and that's the way it had to be. Okay, so now let's talk about derivative of tangent of negative 7x. What's my outside function? Tangent. What's the derivative of tangent?
Secant squared.
Secant squared. So let's do secant squared of negative 7x. So I took the derivative of my outside function, I leave the inside function alone, and now I'm going to multiply by what? Negative 7. Because negative 7 is the derivative of my inside function. And you know, the pretty way to write this, where you're going to see it in like Wolfram Alpha, or you're going to see this written as an answer choice, is you're going to see it written like this, where we move the constant to the front. So it looks nicer. Negative 7 secant squared of negative 7x. So I don't know if I'm going to be this tricky. You know, I haven't written the test yet. I don't know how tricky I'm going to make this test. But one way I could write your answer choice whenever I give you this test, if you had this as a test question, it was like multiple choice. One way I could write your answer choice is actually like this. Did you know that these are the same? Because secant, I'm trying to find some blank space to write in. The secant function is 1 divided by Do you know it, Gabe?
No.
I think is it sine?
No, cosine, yeah. Secant is 1 divided by cosine. Cosecant is 1 divided by sine. It's backwards. But what's special about cosine is that cosine of negative x is the same thing as cosine of positive x. And sine of negative x is the same thing as what? Negative sine of x. Yeah. And the technical term for this phenomenon, when you take the negative of an argument and it remains the same regardless, is we say that cosine is an even function. And the technical term for this, when you make the argument negative, and it's the same thing as making the entire function negative with a positive argument, that type of property is called an odd function. So there's other even functions, there's other odd functions, but cosine is one of those even functions. And since cosine is an even function, that means secant is also an even function. And since sine is an odd function, that means cosecant is also an odd function. And what I'm trying to say here is that, like, if this is an open-ended question, I would give you full credit for doing this, right? That's perfect for an open-ended question, no problem. I would even give you full credit for this, because I don't really care as long as you're taking the derivative accurately. But I want you to know that these are the same because secant is an even function. So it doesn't matter whether you put a negative or not, it's still the same. Okay. Let's talk about this one. This is the derivative of 5x squared plus x minus 1 raised to the power 100. This time, what is my outside function? Everything in the parentheses? Yeah. My outside function is x to the 100 power, right? My outside function, what's happening on the outside of the parentheses is this 100 power. And so first, I'm going to take the derivative of the outside function. And the power rule says, I'm going to bring down the 100, right? And then I'm going to subtract 1 to get the 99th power. And then my chain rule says I leave everything on the inside alone. Just leave it alone for right now. Then I'm going to multiply times the derivative of the inside function. So now the inside function is 5x squared plus x minus 1, everything inside the parentheses. What's the derivative of that?
Could be 10x.
10x, right? Because we bring down the 2. 5 times 2 is 10.
Oh.
And so it's going to be 10x
Plus 1.
plus 1. Because the derivative of x is 1, and the derivative of negative 1 is 0. So that's it. And we are not going to simplify this. Because if we were to simplify this, it would take us years and years off our life. So just leave it like that. Next one, cosine of x squared. What's my outside function? Cosine. What's the derivative of cosine?
Negative sign.
Negative sign. So we write the derivative of the outside function. We leave the inside function alone. And then I multiply times what? 2x. Perfect. Because my inside function is x squared, and 2x is the derivative of x squared. So I could write negative sine of x squared times 2x. Or if I wanted to make it look really pretty, the correct way to write this by convention would be like this. We always put the constant factor first, and then any polynomial factor, and then at the end any trig factor.
Wait, you said what? Sorry.
Again, this doesn't matter to me. Like, in terms of what are yours, you're going to be your grade on the test, this would be full credit, right? I'd give you 100% credit for writing this part. But if you want to know how is Wolfram Alpha, or how is Maple, or how is any professional math type going to write this, they always put the constant factor first, like -2, followed by the polynomial factor, which is in this case x, followed by any exponential function, like e to the x or 2 to the x, that would come after the polynomial. And then after that, there would be any logarithm any logarithm factor, like the natural log or log base 2 or whatever. And then at the end, you list all of your trig factors, like sine of x. So that's the order from left to right that we normally write stuff in. But I'm not going to be picky about that. That is up to you. Depends on how OCD you are. Natural log of tangent of x. What's the outside function? What's the derivative of natural log? Okay. And so I'm going to write 1 over tangent of x, right? Because I'm taking the derivative of natural log, which is 1 over x, but I leave the inside function alone. So it's going to be 1 over tangent now. And then I multiply times the derivative of my inside function. What's the derivative of tangent? Mm-hmm. And again, that's great. This is an open-ended question. Perfect. Full credit. If this is not an open-ended question, if this was like a multiple choice question, here's how I would write your answer. I would look at 1 over tangent and think that's the same thing as cosine divided by sine. It's also the same thing as cotangent, right? Cotangent is cosine divided by sine. The reciprocal of tangent, it's the same thing as 1 over tangent. Secant is 1 over cosine. So that means secant squared is going to be 1 divided by cosine squared. This cosine cancels with one of those cosines. And I've got 1 divided by sine times cosine. That's the same thing as secant times cosecant. And so this is the way that I would end up giving you a multiple choice answer. Even though this is totally correct, it's not how people would typically write that answer. I'm going to write it in the prettiest way possible. Again, you are fine if you just write this for an open-ended response, but I want you to know that these are the same. I want you to know your trig identities.
Those are in this packet.
Uh-huh. Should be. Let me take a look. Let me make sure they're there. Oh my gosh. So they're not really. Maybe I need to make another page of this packet. Sorry, let me be a little bit more clear about what I'm talking about then, because I thought it was in this packet. I honestly thought I had included that. So one thing you should know is that tangent of x is the same thing as sine of x divided by cosine of x. And this is because sine of x, when I define it in like geometric terms, right, we're talking about like a right triangle with an angle x. And this is the opposite side, this is the adjacent side, and this is the hypotenuse of that triangle. Sine is a function that tells me what's the ratio of the opposite side to the hypotenuse. Cosine of x is a trig function that tells me the ratio of the adjacent side to the hypotenuse. And tangent of x is defined as the ratio of the opposite side over the adjacent side. And so if I were to see sine of x divided by cosine of x, this is the opposite divided by hypotenuse divided by the adjacent divided by the hypotenuse. And dividing is the same thing as multiplying by the reciprocal. And then I notice I have a hypotenuse in the numerator and a hypotenuse in the denominator. So those cancel out and it gives me opposite over adjacent. But opposite over adjacent is the tangent function. So that's why we say tangent is the same thing as sine divided by cosine. Then, aside from that, what we should also know is that secant is 1 divided by cosine. Secant is the reciprocal of cosine. Cosecant is 1 over sine. So cosecant is the reciprocal of sine. And then cotangent is 1 divided by tangent. So cotangent is the reciprocal of tangent. And I hope you know that this is how reciprocals work, but just in case you don't, I'll go ahead and spell it out to be a little bit more clear to you. Reciprocal is a two-way relationship. So since secant is the reciprocal of cosine, cosine is the reciprocal of secant as well. And sine is the reciprocal of cosecant. And tangent is the reciprocal of cotangent. Because things that are reciprocals, they come in pairs. They're reciprocal to each other. So those are all true. And that means if I were to see cosine divided by sine, I say, hey, that's the reciprocal of sine over cosine. That means it's the reciprocal of tangent. That means it's cotangent. But you're right. I should definitely type this up and make it part of the packet so that I can be more comprehensive with it. But this would ordinarily be taught in a trig class or the second half of your pre-cal class. And you probably did learn it. You probably just maybe forgot it. Okay, so now we've got that in the back of our heads, and now we understand better what I'm talking about when I say, I think 1 divided by tangent, and so I'm thinking about 1 divided by sine over cosine, which is cosine over sine, and I see secant squared, and I know secant's the reciprocal of cosine, so secant squared is 1 over cosine squared. And then I cancel the cosines, and then I think, what's 1 over sine? That's cosecant, and what's 1 over cosine? That's secant. So I swapped the order of them, but it's still true. Okay. Let's move on. What's the outside function here? Yeah, the outside function, what's going on the very outside of these parentheses is everything's getting raised to the 3 power. And so I think about the power rule for derivatives. That means I bring down the 3, and then I reduce the power from 3 down to 2. Since this is the chain rule, everything else in the inside stays the same. The inside function is natural log of 2x. Does everybody remember what Gabe pointed out earlier? What's the natural log of 2x? Yeah, it'll just be 1 over x. And you can even think about this as being an outside function, where the outside function is natural log and the inside function is 2x. And in that case, the outside function would be natural log, and so that would be 1 over blank. Leave the inside function alone, it's 2x, and then you would need to multiply by the inside function's derivative. And the derivative of 2x is 2, but then, oh wait, the 2's are going to cancel each other out, so that 2 cancels out with that 2. And then in the end, we're going to get 3 times 1 over x times natural log of 2x. Huh?
Couldn't you simplify it further to be 3 times 1 over x squared if the natural log of 2x is 1 over x?
Oh, I made a little mistake. because it's not just 3 times natural log of 2x. This was actually supposed to be squared. Sorry. That was my bad. This is 3 times parentheses natural log of 2x all squared right here. And so that's better. That's how it should be. And this is, I always point this out every day, but this is where we really should be checking our answers. So if I wasn't sure about this answer, maybe I'm a little bit nervous, what I could do is type in the original, which is open parentheses natural log of 2x, close parentheses raised to the power 3. And then I'm going to type in what I found to be the derivative, which was 3 times 1 over x times all of this. And then lastly, I type in y equals f prime of x. And I double check to make sure that my derivative curve in blue is the same as their derivative curve in green. And it looks like it's the same. So that's how you triple check your answer. All right. This time I've got sine of x raised to the negative 1 power. What's my outside function?
X to the negative 1.
Yep. The outside function is the negative 1 power here. So I'm going to use the power rule and bring down the negative 1, and negative 1 minus 1 is negative 2. Since this is the chain rule, everything on the inside remains the same. And I'm going to multiply now by the derivative of the inside function. So I multiply times what? Cosine. And that's perfect. That's the correct derivative. If I was really trying to simplify this even further, one thing I could say is, well, sine raised to the negative 2 power. I know that negative powers are talking about taking the reciprocal, and the reciprocal of sine is cosecant. So one thing I could do is just write this as negative cosecant squared x times cosine of x. And again, there's a lot of different ways in math to represent things. Cosine divided by sine is cotangent. So I could also write it like that. And these are the same. I don't know that one's any better than the other, but always be aware that there's multiple ways to represent the same thing. And now that I'm thinking about it, we used the chain rule to evaluate this derivative, but there's actually another way I could have taken this derivative and not used the chain rule at all. If I had started out by saying sine raised to the negative 1 power is just the reciprocal of sine, and the reciprocal of sine is cosecant, maybe I've memorized the derivative of cosecant. And the derivative of cosecant, I think on your page where you have it memorized, is negative cosecant times cotangent. And so if you have that memorized, you'll notice it should be the same thing. It doesn't matter what way you take the derivative, it should give you the same result. So that way you don't have to use the chain rule if you don't like the chain rule. But you eventually do have to use the chain rule, so you might as well just use the chain rule, I guess. All right, now we've got this one. We're talking about the derivative of e raised to the power negative 2 over x. So what's my outside function? Yeah. My outside function is this e to the power something. And that derivative is still e to the power something, right? Okay. Then I multiply times the derivative of the inside function. My inside function is this negative 2 divided by x. Do you remember what that derivative is?
Natural log. No.
I'll give you a little hint. Remember, negative 2 divided by x is the same thing as negative 2 times x to the negative 1 power. Perfect. Yeah. So when I take the derivative power rule tells me to bring down that negative 1 power, make it a constant factor. So we've got negative 1 times negative 2 times x to the negative 2 power, because in the derivative power rule we always subtract 1 from the power. So instead of be negative 1 minus 1, which is negative 2, and then like you said, like Carter said, negative 1 times negative 2 is 2, and x to the negative 2 power is dividing by x squared, so it's 2 over x squared. And so taking the derivative of this inside function is going to be multiplying times 2 over x squared. So again, we took the derivative of the outside function, left the inside function alone, times the derivative of the inside function. That's the main idea for today. Okay, we've got secant of e to the x. What's the outside function? Secant. What's the derivative of secant?
Secant x times tan.
Yep. The derivative of secant is secant times tangent. And this is important. This is the first time it's happened to us, where the derivative actually ends up with 2 arguments, and you've got to keep the inside function the same, not just one place, but both places. Right? One potential mistake I would see a lot on tests is people write secant e to the x times tangent of x. But no, we need to plug in the inside function everywhere when I take the derivative of the outside function. And then I need to multiply times the derivative of the inside function. The inside function is e to the x. So the derivative is e to the x. So talk to me about this one. It's like a onion. You know, ogres have layers, onions have layers. This has 3 layers to it. There's like an outside function, a middle function, an inside function. And so the first thing we do is we're going to take the derivative of the outside function. The outside function is natural log. And so this derivative is going to be 1 over all of the stuff on the inside of the natural log. Does that make sense? That's the derivative of the outside. Then we multiply times the derivative of that middle layer. And that middle layer is cosine. What's the derivative of cosine? Negative sine. And I leave the inside part alone. And now I'm going to multiply by the derivative of the innermost function. What's the derivative of x squared? 2x. So all together, that's correct, and you would get full credit just for writing that. Don't stress out too much about simplifying if you don't have to. But I see a negative, I see a 2, I see an x, and then I've got sine divided by cosine. That's tangent of x squared. So again, just be aware that that's actually the same thing, since sine divided by cosine is tangent.
So you just did the sine divided by cosine first, and then just plugged in from there.
Yeah, you're talking about like
To get the
sine of x squared divided by cosine of x squared is tangent of x squared.
Okay, so that's just what you did first in your head.
Yeah.
Okay.
So if I had something like this, I can't simplify that
Yeah.
because they don't have the same argument. I cannot write tangent of x cubed, right? That doesn't work. It does not tangent of x. I can't really simplify these into tangent because they don't have the same argument. But if I do have sine of, sorry, I shouldn't have erased all of it, sine of x cubed divided by cosine of x cubed, and they do have the same argument, now this is the same thing as tangent of x cubed. Is that the question you were asking?
Yeah.
Okay. Yeah. So you can make that simplification as long as the argument is exactly the same between them. Mm-hmm. Now, in the next derivative, we've got another triple layer. We've got an outside function, and the very outside most function is everything raised to the 2 power, right? What's that derivative? It's going to be 2 times everything raised to the 1 power. That's how the power rule works. And everything on the inside is sine of natural log of x. Now I'm going to multiply times the derivative of the middle function, the one that's halfway down in layers. So that's going to be the sine function. What's the derivative of sine? Cosine. And I'm going to leave alone everything that shows up on the inside of that sine function, so it'll just be cosine of natural log of x. And now, finally, I multiply times the derivative of the innermost function. What's the derivative of natural log? 1 over x. So, there's not a lot you can do to simplify this, but I think that maybe there's some trig identity with sine times cosine, but let's not worry about it. Let's just call it good. Moving on. We've got sine of sine of sine of x. So let's take the derivative of the outside function first. Derivative of sine is cosine. So I'm going to have cosine of sine of x times cosine of sine of x times cosine of x. Perfect. That's it. I'm just curious. I need to see what sine of x graph says, you know. So we said the derivative was cosine of sine of x times cosine of sine of x times cosine of x. So we got the derivative right because my blue curve matches the green curve. But yeah, that's apparently what it looks like. All right, one more here. One more triple layer dessert. I try to keep my lectures rich with metaphor, from turduckens to onions. And we've got the derivative of arctangent of e to the power negative x squared. So we take the derivative of the outside function first. What's the derivative of arctangent?
1 over x squared plus 1.
1 over x squared plus 1. And I'm leaving the inside function stuff alone. So I'm leaving all of this e to the negative x squared stuff by itself for right now. And then I multiply times the derivative of the inside function. And this time the middle function, the inside function, is e to the stuff, right? And the derivative of e to the stuff is still e to the stuff. And then I'm going to multiply by the derivative of the inside function there. So I multiply times the derivative of negative x squared. What's the derivative of negative x squared? Negative 2x. There's a little property of exponents that we can use here. And that's like if I have a raised to the b power, all raised to the c power, this is the same thing as a raised to what power? B times c. And so if I really was, excited about simplifying this as much as possible, one way that I could simplify this is I could say negative 2x e to the power negative x squared divided by e to the power negative 2x squared plus 1. I just moved the 2 on the inside there. So I do want to repeat myself over and over and over again and just say that like this is fine. If you've got an open-ended question for your response question, that's good.
Could we switch like the negative 2x squared and negative x squared because they're negatives, or would that not work?
Could you switch what? Are you talking about just putting this in the denominator?
Yeah, and then the denominator on the numerator. Because they're both negatives.
So you can't immediately put the whole denominator into the numerator because of this plus 1. That plus 1 kind of ruins that part. But you could multiply the entire denominator by e to the positive x squared, and then just eliminate that factor from the numerator, and that would be okay. Yep. There's lots of correct ways to write things, especially as these expressions get more and more complicated. There become more and more different ways to write them, naturally. So we're still using the derivative chain rule now, but we're also going to combine it with the derivative product rule. You're going to see what I mean right now. Now the outside function is sine, so the derivative of sine is cosine. And I leave the stuff on the inside alone. But now when I go to multiply times the derivative of the inside function is x times e to the x. And so for that inside function, when I go to take that derivative, I have to think about the derivative product rule. So x times e to the x as the product rule. And here's a quick refresher. Whenever I want to take the derivative of a product of functions, This is f prime g plus fg prime. In other words, I take the derivative of one of the functions times the other function plus the first function times the derivative of the second function. And hopefully after the last lesson about product rules, maybe you practiced a little bit, maybe you kind of got used to this, but we're going to say my f function is x, the g function is e to the x, so f prime is 1, and g is e to the x, plus f, which is x, times g prime, which is also e to the x. That's using the product rule there. So this is an example where you need the chain rule and the product rule to fully think through it. I'm just going to show you, if you were using wolframalpha.com to check your answer, this is what they're going to tell you the correct answer is, and it's the same thing, right? It means the same thing. Just factor it out, e to the x. Now, what about this one? E raised to the power x squared times cosine 3x. So we take the derivative of the outside function first, and the derivative of e to the x is still e to the x. So we keep everything exactly the same at first. Now we multiply times the derivative of the inside function. And the inside function is not just one function, but it's a product of two functions. So I've got to take the derivative of the x squared first, times cosine of 3x, plus x squared times the derivative of cosine 3x. So f prime g plus fg prime, I'm thinking 2x cosine 3x plus x squared, and then what is the derivative of cosine 3x? Okay, let's, y'all are close, but let's think about this a little aside. I'm going to change colors so that we can talk about derivative of cosine 3x. The derivative of cosine is negative sine, but then, what have I forgotten?
Derivative of 3x.
Yeah, I have to multiply times the derivative of 3x. So I got to multiply by an extra little 3 at the end. And so, since it's negative, I can go ahead and just make this a subtraction. And then there's going to be a 3 in there, and then sine of 3x, like that. So that was a nice example. It was a chain rule with a product rule inside of it, and inside the product rule there was another chain rule. Just working all the tricks. Yeah, if you think derivatives are tricky, just wait until you're in Cal 2 and you get to worry about antiderivatives. It's a whole nother bag of a...
Just making up stuff.
Antiderivatives is when you work in the reverse direction, and we give you something like this, and you figure out what the derivative was. But you don't have to worry about that right now. Anyways.
Is that next semester when we do that?
We're going to do the very most basic antiderivatives at the end of the semester, but the real hard part comes in Cal 2.
The real hard part.
Yeah. But I mean, you're gonna feel so good when you finally like master this, you know, like whenever you're like really proficient and you can do these fast and you can do these accurately, like you're gonna feel good about yourself. You're gonna finish calculus 2 and you're gonna be like, yeah, I'm like the math expert. Yeah. Calculus is so different from everything you've ever done before, you know? Like in high school, you probably took like an Algebra 1 class and then a Geometry class and then an Algebra 2 class and then a Pre-Cal class. And every single year, you kind of do the same thing over and over and over. Like you talk about functions and you talk about polynomials, you talk about lines and you talk about parabolas and you talk about finding roots and you talk about, you know, factoring. And then you talk about sine and cosine and tangent. You talk about triangles and like you kind of do the same thing freshman year and then the same thing sophomore year, but it's a little bit more. And then the same thing junior year, but it's a little bit more. And then the same thing senior year, but it's just a little bit more. And then you're in calculus 1 and it's like completely different, right? Like you never did any of this before. So it's okay if this is like a hard math class. You're learning a new skill that you haven't been exposed to. And you should feel proud of yourself for every little bit that you can master. So we've got a few more minutes. Let's try to choose something that looks like we haven't seen it before. I love this question. I just think it's one of those hilarious math questions that's so simple once you know what the trick is. But before you know what the trick is, this seems just like really daunting in a way. It's x raised to the power x, okay? That's my function. How do I take the derivative of x raised to the power x? Hudson, got an idea?
I think it's x times x to the x minus 1.
Okay. So I hear what you're saying. You're saying x times x raised to the power x minus 1. And that would be true if we were just using the derivative power rule. But one of the assumptions in the derivative power rule is that your exponent is just a constant number. That's when we subtract 1 and we bring it down and we multiply. But in this case, it's not a constant number. And so it's not going to be the right answer. I know I'm short on time, and so I'm just going to kind of walk you through this. If I have x raised to the x power, there's a certain property of exponents. And that property of exponents is this. E raised to the power natural log of x is the same thing as x. The reason this is true is because we have defined the natural log function as the inverse function of the e to the x function. When you were taking pre-cal, that's just how we defined it. It's the definition of a logarithm. So when I compose the two, composing the two just gives me back the identity function. It's just going to give me x. So this is the same. Now, back here, I can write e raised to the power natural log of x raised to the power x. Because it's still x to the x. There's another property of logarithms we've talked about already, where I can just multiply these two exponents that I'm taking in series like that. E to the power natural log x raised to the power x is the same thing as e to the power x times natural log x. And so when I think about this derivative, what we're really doing here is taking the derivative of e raised to the power x times natural log of x. And this isn't a super easy derivative, but it is a chain rule. And so you start by taking the derivative of the outside function, and then you multiply times the derivative of the inside function. And the derivative of the inside function is a product rule, x times natural log of x. And so whenever I take the product rule, it's going to be 1 times natural log of x plus x times 1 over x. And then this is the same thing as x raised to the power x times natural log of x plus 1. So again, once you know what the trick is, it's like not that hard of a derivative, but like the funny part is like if you haven't seen that before, just trying to think through it. Like it's not just an exponent, and it's not just a power of x. It's something new altogether. You got to really work at. What we see here, the natural log of cosine of x divided by x squared, that's a chain rule because you've got this outside function. The natural log is an outside function, so you'd start with, 1 over whatever. And then it's also a quotient rule on the inside, where you've got to work through the quotient rule. Let's do that one really quick, and that will probably be our entire time for today. So with the outside function being natural log, I'm going to write 1 over cosine of x divided by x squared. Derivative of natural log is 1 over x. And then I'm going to multiply times the derivative of the inside function. And like I said, the derivative of the inside function is going to require the quotient rule, so make sure you have this memorized. It's f prime g minus fg prime divided by g squared. F is cosine, so the derivative is negative sine times g, which is x squared, minus cosine of x, times g prime, which is 2x, divided by g squared, which is x to the 4th. And there's definitely some simplifying you can do, right? Like 1 over cosine of x divided by x squared would be the same thing as if I just flip this around, right? This would just be x squared divided by cosine. And then there's probably some x's you can cancel.